really important to do, which is what I wanted to do, is the reentrancy attack. This is the biggest attack that ever happened, at least directly on this kind of contract, at least as of a few years ago. There have been huge ones since, but they're on layer 2 solutions, like cross-chain solutions. This was the DAO in 2016. It was used to steal $50 million. The DAO was the reason Ethereum was created. The whole point of Ethereum was to be a smarter Bitcoin so you could run code. And they wanted you to create these things called digital autonomous organizations, of which there are now hundreds, which are companies that live on the blockchain. They do not have a board of directors and a president or anything. They just have a computer program running, and they do business. And this was going to be an investment business. So what happened is, it had a flaw, and the flaw was a vulnerability to re-entrance. So they deployed it. They trumpeted for months, telling everybody the DAO is coming, invest now. Everybody invested. They put it up there. People put $100 million in it. And then an attacker stole $50 million of the dollars by exploiting a flaw. So other people analyzed it, figured out how he did it. And the Ethereum blockchain refused to roll back the blockchain because the DAO had crashed. They said, that's not our problem. The blockchain is still intact. The fact that your contract has a flaw is your problem. So the so-called white hat hackers stole the remaining $50 million. So all $100 million had been stolen. And this created a scandal so big that they rolled the blockchain back a month and had a do-over and forked Ethereum, which they were reluctant to do, but it continued. It didn't destroy Ethereum like they thought it might. So this is a simplified version of that attack. And it's called rewards.sol. And we can see how that attack works. And it, again, is just amazing. It's a consequence of this bizarre solidity language. So here's rewards.sol. I'm going to clean off the old stuff and put in the new stuff. Okay. And so here's how it goes. This is going to let you give away some gifts, like rewards you get as a promotion for a company. So you can allow a certain number of gifts, and then people come to draw 1 ether until the gifts have all been used up. So if the remaining number of gifts is greater than 0, it will call the sender and send you this amount, and then it will subtract 1 from gifts. This is the function that lets you take money out, but only until you reach the amount that had been approved and no more. And there's deposit and get balance. So we want to compile this and deploy it. And I'm going to clean off my blockchain by going to Berlin and back to London. So now I got a nice clean blockchain. So now I can deploy the rewards contract here. And in order to deploy the attacker contract, I need the address of the rewards contract. So I'll deploy that here. All right. And so now I've got both contracts deployed. And let me go back to my instructions. All right. So now we're going to look at the withdraw function. We talked about it here. And so what happens here is, if the remaining gifts are greater than 0, then it calls this function sending you an amount, which will send money to the person requesting it, and then subtract 1 from the gifts. The problem is, remember I've talked a few times about how you receive money. The original contract, the faucet, had a receive function that did nothing. This is a bizarre feature of Solidity. When you send money to my contract, I can run code in your contract. When you call my contract with an amount, it doesn't just send the money to me, it runs a function which is under my control in your context. So just sending me money gives me code injection in your code. And in this case, the malicious attacker code is going to recall the withdraw again. So you withdraw it, and then it's going to enter this again and again and again before it ever gets to the -1 step. So it's going to take out more and more and more and more before it ever gets to the line that notices that there's a limit. That's how it works. That's called reentrancy. So here is the fallback function, and here's what it does. It calls withdraw again. So you send me money, and that causes me to make another withdrawal right away. And that causes me to make another withdrawal right away, and this goes on. I've limited it to 10. I could limit it, make it any number I want. And all that happens before you proceed to the next line, which would tell you that I've exceeded my limit of withdrawals. So we compile them and deploy them. And now we fund it. So we have to deposit 20 ether into the contract so it's got some to work with. So we start with the first account and send it 20 ether. And that is to deposit. All right, so now there's 20 Ether in there to play with. Now I think we approve 2 gifts. Yeah, allow gifts. Yep, okay. So here's allow gifts. I'll allow 2 gifts. Transact. That's approved. And now I can see the balance is still 20, and the number of gifts allowed is 2. Okay. Now I'm going to withdraw a gift, and just see it works, just doing it normally. I can withdraw a gift. That works. And the number of gifts is now down to 1, and the balance left in the contract is 19. I can withdraw another. That works. The number of gifts allowed is down to 0, and the balance is down to 18. And if I try to withdraw another, then gifts stay at 0 and the balance stays at 18. It doesn't let me have it. It hits the limit, and it won't let me take out more than 2. So that's what should happen. So now I'm going to approve 2 more. All right. And now we're going to steal 10. So we drew a second gift, tried to withdraw a third, it failed. That's the contract working as intended. Now we allow 2 more, and now we're going to steal 10. So all I have to do is hit attack, and you'll see that it gets 10. So the attacker has a balance of 0. You do attack. Now the attacker has a balance of 10. The original contract has fallen to 8. Even though I was only allowed to take 2, I just took 10. And that's the reentrancy attack in all its glory. And all right, and there's a flag defined in here. So there are ways to prevent this. This, of course, became an important issue. Yes, any platform involving big money needs an audit like SOC 2. I see this comment from Shui, and that's correct. So anyway, here's things you can do. We use this function, address call value, and that is a function that has no gas limit. So one thing to do is instead use send or transfer. Those have a small gas limit, so you cannot just, you made one call to it and it tried to do a bunch of transactions. It would run out of gas before doing too many. So this is one way to prevent it. There's other ways to prevent it. One way is to just rewrite this function. And this is one way to do it. Subtract 1 from the gifts before you go, and only let him have 1 if the gifts are still a reasonable number. Remember, when I subtract 1 and it goes below 0, it will turn into plus infinity, and then this will fail. So this is another way to do it. If you just change the order of the statements, where the first thing it does is see if there's remaining balance and then send it to you, that even if I keep re-entering it, it will hit this if statement and subtract from gifts every time, so you won't be able to draw too many. Here's an alternate fix that looks a little better. Just subtract 1 first. Only go if gifts greater than 0, then gifts minus 1. This way you avoid that sloppiness of using the plus infinity. Anyway, those are 2 ways to do it. And if you modify the contract that way, it will no longer be vulnerable. So I wanted to show you that. And I think that's enough demos for tonight.